Welcome everyone to today's lecture on partial differentiation. I've put up here a map of the big island of Hawaii, and some of you may be familiar with this sort of map if you've done some hiking, perhaps you've used one. This is a contour map which shows the elevation at all the different points on the island, and these lines represent they're lines of constant elevation. And what you can see here is these circular features are the volcanic mountains that compose this island. Now you may be wondering what this has to do with calculus, and the answer is that what we want to do today is extend our notions of calculus to functions of more than one variable. So we're used to doing calculus with single variable functions, and we want to think about functions of multiple variables. Now, in general, it can be difficult to visualize functions of many variables, but it turns out that if we have a function of two variables, there's a very nice way that we can visualize these. So we can visualize a function of two variables as a landscape where x and y gives your position, and the quantity f of x and y gives the height of that position. And so we're going to use this sort of picture today to build up our intuition about the mathematics of functions of many variables, and when we do this, we'll be able to generalize it more easily. So to start out, let's just review a few facts about differentiation in the single variable case. So here I've just plotted the function f of x is equal to x squared, and recall that the derivative of a function at a point is given by the slope of the tangent line at that point. So at the point x equals 0.5 here, I've just drawn the tangent line, and the derivative of that point is just the slope of that point. Also recall that one of the useful things that we do with derivatives is we can use them to find stationary points, maximum and minimum of functions. And we do this by solving the equation df dx is equal to 0. So just as a warm-up, by show of hands, can people tell me for which point x in this figure does df dx equal 0? So if you think the answer is x equals 0, just raise your hand. Okay, good. And does anyone think that the answer is b x equals 1 or c x equals 2? Okay, no, that's good. That's correct. The answer is x equals 0. And you can see that just by thinking about the tangent line at x equals 0 would just be some horizontal line, and the slope of the horizontal line is 0. And also this corresponds to the minimum of the function. So with that review, I now want to go to thinking about functions of two variables. So here I have plotted some function of two variables, x and y. We can just sort of rotate this around to look at it from different angles. So it's some sort of mountain or hill. And the main point I want to make here is that imagine that you're standing somewhere along the side of this hill. And you can imagine, say, walking around this mountain, not going up or down in elevation, but just staying at a constant height. Or you could imagine walking up the hill or down the hill, in which case your elevation would be changing. So depending on which direction you're going, there's a different slope. And we can also view the same information on a contour plot. So this is showing just the same information in a slightly different way. So imagine you're now looking down at this function from the top, and these lines represent they're lines of constant elevation. So once again, you see that you can walk around in a circle and not be gaining any elevation at all, or you can walk perpendicular to the lines, in which case you'll be going up or down this hill. So now we just want to formalize these notions of going in different directions and having the slope being different. And we do this using what are called partial derivatives. So the partial derivative of f with respect to x would be the slope of f in the x direction at a fixed y. And the derivative of f, the partial derivative of f with respect to y would be the slope of f in the y direction at fixed x. And note here, there's just a small change in notation from what you're used to in the single variable case. In the single variable case, you have dx, and here we have this curly d dx. And this is just to remind us that when we're taking a partial derivative of a function, we're keeping all of the other variables held fixed. But besides that, actually computing partial derivatives is very, very similar to what you are already familiar with in the single variable case. There's really only one additional rule that you need to know, which is to treat all other variables besides the one that you're differentiating with respect to as a constant. So to show just exactly what I mean by this, I'd like to work a simple example. Let's consider the function f of x and y is equal to 3x squared times y. So if I take the partial derivative with respect to x, I'm holding y fixed. So that means that y is just a constant in the same way that here that 3 is a constant. And recall that the derivative of x squared with respect to x is just 2x. So the result then is just 6xy. Similarly, I can take the derivative of this function with respect to y. And when I do that, I'm holding x fixed. So x is fixed, or considered a constant, and that means x squared is also a constant. So these just come on. And then the derivative of y with respect to y is just 1. So the answer here is 3x squared. That pretty much concludes the lesson for today. I just want to recap what we've gone over. So we've extended the notion of differentiation to functions of many variables. And we've done this by starting out considering just functions of 2 variables, x and y, because it's easy to visualize functions in this way as some sort of landscape where the quantity f of x and y gives the height at the point x, y. We've then sort of formalized this notion of slopes in different directions using the partial derivative, where the partial derivative of f with respect to xi gives the slope of f in the xi direction. And we've learned how to calculate partial derivatives by, to take the partial derivative of f with respect to xi, we treat all variables except xi as a constant.